Okay, thanks for coming to this talk. It's a proposal for a vendor-agnostic pipeline for ONOS and Stratum. Okay, first about who we are. Okay, my name is Alan Lowe. I'm a software architect at Mellanox, working in the advanced development group on switch architecture. I'm primarily responsible for the compiler backend generation for our Spectrum and Spectrum 2 line of programmable switches, and also the P4 runtime architecture and prototyping. And a lot of this effort in this presentation was also driven by Matti Kadosh, our principal architect, who's responsible for all things relating to switch programmability in our group. Okay. All right, so our motivation for proposing a P4, what we're calling a generic modular switch architecture, or GMSA, if you read the abstract, or if you didn't, boils down to five main points, which I'll go over in the following slides. But I just want to make sure we define the terms generic. By generic, I mean something that works on multiple vendor hardware, okay? And modular in the sense that standard components that are commonly used in switches are abstracted, okay? All right, so the next slides come from, these 5 observations come from over a year of working with P4, and our observations are following. So we've seen that most of the current P4 programs are based on the V1 model, and depending on how that program itself is written, it can require substantial effort to map to an ASIC. Okay? From the user point of view, the V1 model is great because it's for greenfield deployments, because it prevents a nice clean slate, lots of possibilities to write exactly what you want. Some downside may come that later the P4 programmer may find that they need to re-implement standard functionality that's present in most switches, like L2 bridging or L3 routing or MPLS forwarding. Okay. From the vendor point of view, the V1 model maps well to software switches, and not necessarily is a suitable model for a compiler backend that generates towards ASIC hardware. Okay. Except for perhaps Tofino, right? So from what we've experienced, it can create a lot of effort for hardware vendors. The V1 to hardware target mapping is often not straightforward. And then also on one side, it does require some compiler expertise that not all vendors may want to invest heavily in. So that creates a somewhat high barrier to entry for vendors to enter the P4 area. Okay. And in this slide, I'm showing the current state of the P4 runtime view and actually what we've implemented on the Spectrum. So each vendor needs to implement their own P4 runtime agent. So for example, here we have the SDN controller. It can load a couple programs like Fabric P4 or Tor P4. The platform, agnostic parts, GNMI, and P4 runtime are up there, but then all the blue, the vendor needs to implement. We implemented our own GNMI, specific code, plus P4 runtime driver for Fabric P4. Okay? And that all lays on top of our SDK. So most vendors would have to do something similar. Next. Okay, so now the motivation for a generic model here. So to make the P4 runtime layer vendor agnostic, what exactly is needed? So one thing that would help is a common pipeline used across all vendors. Okay. So such an exercise was performed by the Psi community, and out of that came something called the Psi behavioral model. Okay. I believe Brian mentioned that in his first talk on Stratum on Tuesday. Okay. So in this sense, we're proposing Psi. Psi itself is not a goal. It's a means to an end. So for example, the real goal is to have a generic pipeline, and the Psi behavioral model happens to satisfy those requirements. Okay? Even though it is, I think as Brian said, a least common denominator. Okay? But what we found is that least common denominator does manage to address many use cases. So in the end, what happens to the P4 runtime implementation? Instead of the parts in blue, the GNMI and the P4 runtime is written against a generic library, the Psi library. And any extensible parts in the blue now would be the parts that the vendor needs to focus on. Okay. So for example, when we went through the exercise of looking at Fabric P4 and how it operates as a spine, it turns out all that functionality was totally generic and would fall down the gray side. Okay. Whereas if we implemented the Tor part of the Fabric.P4, the small blue part would be like the support they added for INT, and that would come through instead through the FlexI in the blue on the side, and that we would handle specially. Okay? So if we had this type of infrastructure, then our effort to get our switch up running with ONOS and Fabric P4 would have been a lot faster. Okay? All right. Whoops. Let's go next. Okay, so here's the pipeline example for a hybrid NOS. And as I mentioned, there's Tor.P4 with the extensible part. And the idea here is that this pipeline at the bottom, same one that actually Brian had in his talk, this can either describe a fully programmable hardware or a fixed function pipeline. The idea is that it's common. The flexible points, not all hardware needs to support those, but they do need to support the, obviously, parsing, deparsing, and the black parts. Okay? And I'll talk about each part in a separate slide. Okay? What you need to note is that the P4 runtime layer lays above everything. Okay? So that part is agnostic to the details below, whether it's SI and the vendor SDK. Okay? On the left side would be the legacy functionality. Okay, and on the right side, it would be just the blue part, which would be the extra functionality like INT, which you've added to your Tor.P4. Okay. So the key point here is that a common pipeline enables this, this approach. All right. Okay, now I'm going to discuss some of the details for what we propose as a generic behavioral model here. So there's the pipeline again. Okay, so the idea is that a generic target will help us deploy new hardware by running the same application stack across all vendor hardware, or at least all vendor hardware, in this example supported by SI, in a consistent, enabled by a consistent and simple programming interface. Okay, so this model consists of 3 parts: read-only blocks. So those are fixed function, and they may or may not be described explicitly in P4. But the point is they are not modifiable by the P4 program, so you don't necessarily have to have them in your P4 program. And I'll discuss a little later why you might want to have them described there. Read-write blocks. These are predefined functions that may be altered by the P4 program, but there would be a well-defined common default, for example, for the parser and the deparser. Okay. And then the green blocks, those are user blocks. These are optional programmable functions as defined by the user. And they can be inserted at those specific points. Okay. All right, so diving into some of the P4 kind of high-level architecture, there's the package definition for GMSA. So in contrast to the V1 pipeline, which is basically ingress egress, we split up a little bit more. This pipeline proposes a set of headers, standard headers that do not change. Okay, you can introduce new ones, and the idea would be it would be standard. And having in some discussions, this could even be part of a like the PSA spec, where all P4 programs use the same standard headers, so the syntax is the same across all programs. Okay, parser. So we give a basic standard parse chain. The user can modify by adding headers and transitions, and the same thing for a deparser. Okay. There should be a generic set of actions, GMSA actions here. So for example, we would take all the actions supported by SI, which have been agreed upon multiple vendors as common actions, and we'd take that as the initial base. Although vendors can extend by adding their own actions. Okay. A similar way, metadata used in P4 would be standard metadata that's common to all the platforms, so there'd be a standard metadata object there. Okay. And by stage, it means you'll have different metadata at different stages in the pipeline. Okay. Okay. So stepping through each control, there's the control parser, that's packet in, packet, and then generic metadata, and then out packet headers. That's pretty straightforward. So in the parser, you can add nodes, remove nodes, create new transition between nodes. After the parser is the black part, which is the port. That's the read-only part. So here, it's not explicitly shown in the package level. And that's not there because the P4 programmer can't modify it. Okay. However, it's possible you might want to define it via like an extern, just so the control plane can reference it. And this is kind of an artifact that the P4 compiler is used to generate both the binary blob for the platform and also the P4 info. So if we include it in here in the package definition, then you could use that for P4 info towards the controller. For simplicity, I excluded it from here since it would make it quite a bit larger. Okay. All right. Okay, so the next stage after port would be the user-defined ingress port. Okay, there we'll take in headers, generic metadata, and then ingress port metadata specifically. Okay, so the generic metadata, as I mentioned earlier, is valid for all stages. And it would contain common information across all parts of the pipeline. The import metadata would contain only metadata that's valid for the ingress stage, like an ingress port or a VLAN or a lag ID, things like that. Okay. And in here, there's probably a requirement for some custom metadata, and there's a couple ways of doing that. We could add it either directly as another parameter in the control, or it could be tagged on top of the import metadata as the last field, a custom struct. Keep in mind that there's probably a need to have per stage custom metadata. Okay, so you can see part of this is still work in progress as we're working out the details. Okay. All right, so we've passed the black bridging stage, which is the L2 bridging, which is a fixed function, and then after that comes the ingress riff or ingress routing. Okay, this comes before routing. It has the same generic metadata and ingress routing specific metadata like router interface, VRF. So for example, if you want to do a match action on VRF field in the metadata, you would have to do it in this location, and it would only work in this location because that's the only place where you get the ingress router metadata. That would prevent someone from trying to access VRF earlier, it's like an ingress port. Okay. So similar goes for post routing. So I won't step through the rest of that because it's the same idea. Okay. So this slide is adapted from Brian O'Connor's presentation on Stratum on Tuesday. Okay, so it shows the general architecture of the Stratum switch agent. The top part in green is a hardware agnostic layer. The three usual pillars, P4 runtime, GNMI, GNOI, presenting standard interfaces, and a switch broker interface to handle that. Okay. The interesting part for us is the, I'll call it yellow, chip-specific area. So in the Stratum project, each vendor would need to implement various hardware functions as node and table managers, port management, things like that, all specific to the vendor, in this case, vendor X. They would write all those functions. They would bind them against their vendor SDK or the SDK adapter, depending on how the architecture works. And the same thing, and there's also a platform-specific layer, which may be different from the vendor, chip vendor. But the idea here is that for the next chipset, they would have to do the same thing for vendor Y and vendor Z. So the difference between this and using a common pipeline and a generic target would be with the blue. Okay, so we replaced that implementation with GMSA functions support for the basic, we can call them legacy, ACL, ECMP, FTB, next hop, L2 tunnels, things like that. Ports, interfaces, QoS, and those would all go through the SI APIs. Okay. And the nice thing, at least from vendors' point of view, is that then, oops, let me, down there in the chip-specific part, the vendor need to only focus on the lower part, which is kind of where SI glues to the vendor SDK. Okay. At least most of their effort will be spent there. Okay. All right. So the next thing I want to talk about is some of the use cases. So beyond the proposal and the initial model, I want to move to some real working prototypes that use this GSMA architecture. Okay. The first one is called bare metal Tor. It's adding bare metal services to the cloud. This was presented by us in the OCP Summit 2018. Okay. I'm not going to go over the details. I'll just highlight the overall use case to emphasize how this model has helped implement this very quickly and easily. So the goal is to connect bare metal machines to the cloud VMs. And the challenge is scalability in tunnels. So we used a flexible, non-standard overlay that addresses this scalability. And if you have more interest in this, you can talk to me later and I can show you the OCP demo. Okay. But the key point is that the standard underlay is just managed by BGP. Okay. So how would the pipeline look like for this? So this is a vision of the pipeline. So you would have a controller like ONOS who would manage the VM Tor part of the application. Before runtime, it would load down the VM Tor pipeline for the flexible tunnels. And the rest of the side is managed by FRR. Okay. So this is what we refer to as a hybrid mode. Okay. So the focus is just on this side is of just what we need to do. Okay. Second use case. So this seems to be a popular one. I was reading the talks last night, and I see Mario has the same use case in his talk. Okay, so it seems to be a popular one. This one we presented in IBC 2018. It's time switchover. So what's happening in this use case is, you can imagine this is like an ESPN video event, and they have high definition cameras, sending video streams to various monitors, and then they're switching between cameras. Okay. So the need is to make a clean switchover. By clean, I mean they want to switch over from a camera to a different camera at the end of a video frame, not a packet frame, a video frame. Okay. All right. The current implementation uses IGMP at the endpoint. So the endpoint receives the new flow while receiving the old flow. So it buffers both streams, and when it's ready, it switches frames. Okay. The downside for that is obviously the endpoint needs to reserve twice the bandwidth to hold both old and new streams. And the endpoint needs to buffer all of this, which is a lot of memory and may cause some latency effects. Okay. So in this hybrid approach with this pipeline, the implementation will go as follows. We match on the RTP timestamp that's received in the media streams. Okay. So the idea is that in RTP, all the packets that belong to the same video frame have the same RTP timestamp. Okay. So we can do a range match on that. And the advantages it has is with a hybrid pipeline, all the legacy protocols like IGMP, PDP, PIM, whatever is needed, are operational alongside the flow switch, time switch implementation. Okay. So no effort needs to be kind of put into describing that in P4 and getting all that. Okay. The endpoint links then carry only the relevant information and as it's switched atomically at the right part in the frame. Okay. And this reduces buffering and latency issues. And the pipeline. So same idea. right? You have a switch time P4, some controller loads it, P4 runtime. This time there's two parts in the pipeline. There's the parser plus a custom RTP header. And then we match action table for the switch time, which uses that information. And then the rest of the bridging, routing, and the policy, that's all supported by, in our case, ONX, any ONOS, okay, doing legacy functionality. Okay. So this is what we mean by a modular pipeline, okay, that operates in a hybrid mode. So it's not pure SDN, it's not pure legacy. Okay. And the final thing I just want to show is, so this is the P4 program, which we, almost all of it, I think I took out one small piece for the UDP, but this is just about all of it for the time switch program. You can see there's 4 actions at the top, 2 tables, there's actually 3. There's a UDP port table, which just couldn't squeeze in. But that's all. So there's a table for a match action on the timestamp. There will be another one for the UDP port for RTP. And then there's the multicast forwarding. Okay. And then there's nothing in the other control points, and that's all. Okay. There's a few custom actions there to set a range bitmap and to do policy-based switching. Okay. Similarly, for the bare metal Tor, this is all that was needed. Okay. There's two match action tables, one for VNet peering and one for tunneling. And some actions to support that. One to set the VNet bitmap and one to action to the tunnel, set the bridge and then put the VXLAN tunneling cap. Okay. So the nice thing about this is that's all. You don't have to describe anything else in the system. This is just the additional parts. Okay. All right. Okay. I think that's all I had. Thank you. And any questions? Okay, this one. You guys, go ahead first.
An example, where would the P4 info come for the implied part of the pipeline?
So that part, the implied part of the pipeline was not managed by ONOS, so it didn't need it. It was managed by, in this case, just by the ONOS. Okay? So in cases where you would need it, then we would describe it in P4 and have it there just for the P4 info to actually pick it up. Okay. All right.
Thanks, Alan. So first, I'm very supportive of how can I say, a standard P4 runtime to site translation in Stratum, and I think Stratum should be P4 architecture independent, so should support any new architectures. I have a quick question though. If we go back, going back to one of your early slides, you don't need to go back, but it's a slide where you show the Stratum architecture with P4 runtime being translated to, there's a fixed SCI part and then there is a SCI extension part. It's one of your early slides.
Yeah.
No, it was before that. It was the first, with there was the Tor.P4 with a little blue box, which you said was the INT part.
Yes, okay.
So my question was, for the part which is not standard SCI, yeah, exactly, thank you.
Yeah.
For the part which is like P4 runtime to flex SII, do you think we actually need to use like SCI extensions and auto-generate those SCI extensions from the P4 program, the programmable parts? And if you do think so, why do you think there would be any value in actually using the SCI extension mechanism for those programmable blocks? I hope that makes sense.
Is it needed? In a sense, it would be needed because SCI doesn't have any notion of these extensions.
Yeah, but
right?
Do you think we actually need to go through SCI for those extensions, for those new features?
No, you wouldn't need to go through SCI.
Or we can do P4 runtime to vendor SDK directly.
Yeah. So this was, for example, we actually did this in Sonic, where Sonic has lots of SCI in it. So we built, there's a SCI, Flex SCI compiler, generated the APIs, and then we built it off that. But you're right, it doesn't actually have to go through SCI at all.
Okay, good.
Okay. But since the underlying system was using SCI, not a SDK.
And as far as GNMI for the management interface, do you think that SCI, would you say that SCI is a superset of GNMI, or would you say it needs to be for management, or would you say it would need to be extended, like in terms of port and QoS?
Okay.
Because in one of your next slides, you did show GNMI and some vendor agnostic code like going into a Psi box.
Yeah.
And so I was wondering if you think Psi is enough for all of GNMI.
Probably not, would be my guess. I haven't looked at it closely, but we'd have to do a comparison line by line. I haven't done that.
All right, thanks.
Oh, sorry.
Hey,
Sorry.
hey, Alan, thanks for the presentation. Yeah, my question. Yeah.
Okay,
I'll
go
get
ahead.
to you after that. So it seems like either, I mean, this is exactly what current Stratum in its current form is doing, right?
Yeah.
It's defining it's a pipeline which works for most of the switches, right? Which currently we are supporting for Stratum. Now, either we extend that to include the new blocks which GSMA is bringing in. That's one option.
Yeah.
Second option is go to Psi community and enhance their pipeline, right? So here the idea is that we're trying to come up with a pipeline, even Psi or Stratum, in current form, as of today. It's not limited to only that pipeline, Stratum, right? Doesn't want to be limited to that pipeline. But this idea of trying to come up with a standard pipeline is what, was the problem which P4 was trying to solve, right? So now, because P4 is so generic, it can support any pipeline which anybody can imagine.
Yeah.
But it can't be mapped easily. That's the problem, right?
Yes.
Now, this is this the only way to solve that problem? Or
Oh, no. Certainly
okay.
not.
If this is the only way to solve the problem, only for fixed function ASICs, and so you're proposing it only for fixed function ASICs and the ASICs which are really limited in which can be mapped easily to this pipeline. Let me complete that. So
Yeah.
now for the FPGAs, NPUs, right? So are you proposing only for this this kind of ASICs which are in a way fixed, or for everybody?
No. So this isn't for everyone. So I don't know if I have the diagram, but here you go. So in the Stratum presentation, like, this is what the vendors need to do. So if you want to go off and support your ASIC or your FPGA, which has tons of great features, then you do that. Okay. Now, I think the problem is that there's a lot of legacy hardware, or there's a lot of other hardware vendors who don't want to put in that much effort, or they see this as a big barrier to entry to Stratum. Okay? So this is a great way of starting off and saying, okay, I understand, as I think Brian mentioned, it's least common denominator. It's a smaller subset of functionality. But this at least gets the hardware in to the project. Okay? And then if it gains steam, then it might be to the vendor's best interest to get rid of Psi and actually start doing all of that themselves. Okay? But it's kind of like an incremental approach. Some vendors might want to just stop there because all they support is fixed function, and that'd be fine. Okay? But certainly it's not one size for everyone. Okay? All right, sorry. Last.
Just one more question. Yeah.
Sorry.
I think it's a quick one. If I understood correctly, the parser is one of the blocks that are fixed in your architecture.
It's not actually fixed. For some hardware, it probably will be fixed. For other ones, it might not be.
Okay.
Okay? And then there's a kind of a hybrid in between where if you have certain capabilities, you could have a limited parser, which has some expandability. Like, you might be able to add terminal nodes, if you know what I mean, like terminal protocols, which are just extensions of that don't have a next protocol after that. You can do that simply.
Okay. And you needed that in the second use case?
Yes,
or not?
yes, exactly.
Thanks.
Okay. Well, okay.
So how does this architecture helps you in upgrades, specifically for upgrading vendor X SDK, version X, version Y, version C? Does it give you more leverage in terms of like middleware agnostics upgrades, or you still have to go through the Psi upgrades as well because of, again, site dependency on SDK?
Right. I suppose if the vendor SDK upgrades, but it doesn't change the Psi APIs, then you're fine, right? It's the usual. I don't think, we haven't solved any problems in terms of upgrades. It's the same Stratum approach.
Okay, and in the hybrid switch mode that you're doing, there's like half legacy, half
Yes.
SDM based. do you also have you done any kind of like investigation how to upgrade half of it only, or basically it has to upgrade the whole pipeline?
Well, they're essentially separate, right? So if you need to upgrade your PGP, that's
No, but the
that's
pipeline is fixed. The pipeline is common between the legacy half and the
Yeah.
and the
so-
SDM based half.
Okay. So there's the fixed function parts, which P4 doesn't even see. So if you upgrade it, that's separate of it. It's totally separate. Okay.
Thank you.
Okay. Thanks.